This video is going to repeat the analysis of the prior video, which is find the time to drain for a tank with starting depth 3 meters until depth equals 0.5 meters. So we've just done this one, except this time, instead of doing analytical integration, once we've built the continuity equation, we will actually use a numerical method to approximate the solution. And what we'll discover is that with sufficiently small time stepping, we obtain nearly the same solution as we would analytically. The point being that for complicated geometries, numerical approach might produce a reasonable answer in a shorter amount of elapsed human time. So let's repeat our tank again. We have an outlet with a diameter of lowercase d. We have a circular tank with diameter of capital D. Everything starts off with a free surface here, and then it drops as time progresses. And we're going to use as the approximation the outflow geometry that the velocity equals the square root of 2g h, where h is the value at time t of the free surface. Okay, so we're going to let the control volume equal volume of water in tank at any time t. And the control surface will be the bounding surface including the outlet pipe. So here is my control volume in green, for lack of, currently only have 4 colors to work with. So there's my outlet. Remember in class we said indicate the outlet vector and the velocity vector. And that will help us get the signs correct. Green guy is our control surface, and in this case we will find it advantageous to keep track of the velocity of the free surface, dh dt. Alright, there's our basic setup. Now we'll apply continuity and see what we learn. Continuity analysis says that 0 is equal to the time rate of change integral of the control volume of rho d volume plus the integral of the control surface of rho v dot dA, where those are vector components. First one, the time rate of change of the mass in the control volume, d by dt of the integral over the control volume of rho dV is equal to rho d by dt of pi capital D squared over 4 times h of t. Rho is going to be constant because we're dealing with water, and so this can be more or less reduced to rho dh dt multiplied by pi d squared over 4. No need to really rearrange it much more than that. The integral of the control surface is rho v dot dA, which in this case is rho times velocity out, area of the outlet, and that equals rho times the square root of 2g cap h times pi lowercase d squared over 4. Now we substitute these back into the continuity equation. Basically, we replace the right-hand sides. And we have 0 is equal to rho dh dt pi d squared over 4. And the control volume is getting, well, we'll just leave it at that, plus rho square root of 2g cap h pi lowercase d squared over 4. We'll cancel what we can. Density is constant, so those rows can be canceled out. Pi over 4 is a constant, so that can be multiplied out. And what we have left is minus dh dt equals square root of 2g cap h times d squared over capital D squared. Okay, what we did last time is we separated and integrated from this point forward. Instead, what we're going to do is we'll approximate this with a numerical method. So recall from calculus that the limit as delta t goes to 0 of h at t plus delta t minus h at t over delta t is the definition of dh dt. So now what we'll do instead is we won't run the delta t to 0. We'll actually use this difference equation, this difference quotient, h at t plus delta t minus h at t over delta t, as an approximation for dh dt in this differential equation. So let's first move the minus sign to the right. So dh dt is equal to minus square root of 2g d squared over cap d squared. That's all a constant. Times the square root of h. Now we'll replace dh dt with its finite difference approximation. So the left side is h at t plus delta t minus h at t divided by delta t equals I don't know what to name this constant, so we're going to name it alpha equals minus alpha h of t to the 1/2 power, or we could have done square root of h. Okay, now clearly delta t has to be small, and how small is really a matter of, for practical purposes, trial and error. So keeping that in mind, let's make a few more manipulations of our difference equation, and then we'll go ahead and code it into R, and we'll see what kind of answer we get. Okay, so here's our difference equation that we're going to want to code into R. We have h at t plus delta t equals h at t minus delta t times the quantity alpha h at t to the 1/2 power. If we look at the right-hand side, at any moment in time, we should know these values. So we put the current values into this update equation, multiply this by the delta t, subtract that off of the current value, and that gives us the new h at t plus delta t. We also need to specify that alpha is equal to the square root of 2g multiplied by the diameter ratio squared. So our inputs will be lowercase d, uppercase d, value for g, and h0, which is h at t equals 0. And then the last input we need to provide is delta t, and we can let the program estimate the depth as time is marched forward. We'll also need to input some logic to stop when h is close to, I guess we'll add another input, h min. Okay, so with that, we can now attempt to come up with an R script for solving this. And I'm just going to go ahead and hard code in the various inputs, and I'll leave the making generalization up to anyone that wants to. Let's get good and in focus. Okay, for this problem, I'm using RStudio. And we'll go ahead and use the entire screen because we can. Don't like that. Okay, that'll work. So first thing I need is I'm going to need a